Right, so we went into chapter 15 and we started talking about these vector fields, and we learned a lot of language in 15.1 about a vector field can be conservative, and if it is, then you can find the potential function, and that means that the vector field is the gradient of that potential function. We can do a curl of a vector field. We can do the divergence of a vector field. Those are operations we can do on a vector field. So we kind of learned all that in 15.1, and that's good to get to know vector fields. But when you move to 15.2, it's kind of a little bit new topic here. In 15.2, we do something called a line integral. They're called line integrals, although it might be more appropriate to be called curve integrals, where we're integrating along a curve, but anyway, we call it a line integral. the line can curve. You know, it looks like this. We're going to do a couple different types, but the first type is we say we're doing an integral over a curve. This is called a line integral. We're integrating over a curve. We're going to integrate a function of x's and y's with respect to s. And s is always used as the arc length of the curve. So we're integrating sort of with respect to the length of the curve. We're integrating some function with respect to the length over some curve. I mean, this is a new type of integral. You know, what have we done in our calculus life? We've done these kind of integrals. We've done an integral from a to b of a function. You know, can I just say that what you're doing here is you're integrating a function over an interval on the x-axis. You know, you're integrating over an interval on the x-axis. And then, that was kind of the only kind of integral we did for a while, but then we got into double integrals over the region R, you know, with respect to the area of region R. I mean, so then we were integrating over a region, right, you guys? Maybe there was a function in there, but you're integrating over a region in the xy plane. So now I'm integrating over a curve in the xy plane, or this could be in 3D, and I could be doing a curve in space. I could be integrating along a curve in space. So I guess that's why it's a single integral. You know, when you integrate over a two-dimensional region, you needed sort of a double integral to integrate the two-dimensional region, or to integrate over the two-dimensional region. But now I'm just integrating over a one-dimensional curve. These curves are given parametrically usually. We should try a problem, I think. This is it. By the way, just to look at that problem. There is nothing about a vector field in this problem. There is nothing about a vector field in this problem. So the second type of line integral that's also introduced in 15.2 is this one. I want to do that one first, but I'm just previewing. Here's another one. Another line integral where you're integrating over a curve, but now you're integrating the vector field dot dr. So this is this is actually a more important line integral here, and when we get around to our test, it'll be full of these. There might be one or two of these, but it'll be more of these. But let's fight through this guy first here. So let's see, what can I do to you here? I can give you a function. Let me give you a function. I'm going to integrate a function. I'm just making a kind of an easy function there. And then I got to describe a curve to you. So here's this curve. Now watch this. This is kind of interesting. I'm going to describe this curve to you by giving you a picture. My curve is this curve. It goes from 0, 0. When you have a curve, there's a certain orientation to the curve. So the way you travel on that curve means something. So I'm going to go to this point, 2, 2, and then actually I'm going to go over here to this point, 4, 2. I'm going to go to this point, 4, 2. This is the point 2, 2. And you can integrate these curve integrals, these line integrals, over a curve. The curve has to be, they say, I think they start off saying maybe the curve has to be smooth. But then they quickly say, wait a minute, it doesn't have to be entirely smooth. What it has to be is piecewise smooth. So this curve is not really smooth. It has this sharp point, but in pieces it's smooth. If you looked at this piece and then looked at this piece, they're smooth. So, and the truth is, it's kind of two separate curves. When we talk about these curves, we parameterize them. And so again, this is sort of why I told you this chapter 15 is kind of a good review chapter. I got to go back and I got to think about parameterizing these curves. But what I've decided here, I think, though, is that to do this problem that I've set up here for you, I've got to split this curve into a C1 and a C2. And that means I really kind of got to do two separate integrals. I got to do the line integral for C1 of this function, ds, and then I got to do the line integral for C2 of this function, ds. So that's the first thought. I got to do two damn separate integrals. Excuse me, I got to do two integrals. All right, well, let's work on C1. And so for C1, what I want to do is parameterize it. Okay, so I have to parameterize C1. So that means I got to come up with parametric equations. You know, x equals some function of t, y equals some function of t. What do you think that might be for this path C1? I'll tell you what, let's start with this. What would be the rectangular equation for the path of C1? What would be the name of that rectangle?
Y equals x.
Good. It's good old y equals x. Right. That's the rectangular equation, y equals x. Now, okay, you're right, y equals x. But how would you then parameterize that?
0 to 2.
Well, let x equal t, and then y is, if x does equal t, then y is t. Okay, good job. We just parameterized it. Oh, and then how much t do I need to finish C1? I need t to go from 0 to 2. Thank you. 0 to 2. Are you guys okay? This is some brand new work here. I mean, we started in 15.1 yesterday, and we talked all about vector fields, and now I'm leaping into 15.2. We got to do these integrals, these line integrals. But this is all good stuff. Everything I'm doing is very relevant to the rest of this chapter. We need to set up parametric equations, look at pictures, come up with equations like this. So I'm going to start setting up this integral here for C1. And so guess what? So because what happens then is what you do with these integrals is you turn them all into t's. Everything gets turned into t's. So here I go. You already decided okay, so since x is t and y is t, this is going to be a t squared plus a t squared. By the way, that's a 2t squared is what that is. I got to teach you about the ds. The ds is a little tricky. Hang on. What about bounds? If this is all going to be in t's, what do you think the bounds are?
0 to 2.
0 to 2. Thank you. Okay, the ds. What the heck is ds? They show up in these integrals, so we need to know about this ds for these integrals. By the way, when we move to the new other type of integral, we don't have ds. It's different, but we need it for this. What is ds? Well, I told you S represents the arc length of the curve.
Magnitude of the
Good. If I remember what arc length is, I have to maybe remember that arc length was an integral itself, and it was the integral of the magnitude of, oh boy, of r prime of t dt. Now, all of a sudden, I just switched notations on you a second here. Now listen, I just used that r of t notation. This wasn't r of t notation, this was parametric equations. Well, this was parametric equations. X as a function of t, y as a function of t. The truth is, this was sort of chapter 10, parametric equation notation. When we got to chapter 12, we used vector-valued function notation. Listen, you guys, I can describe this curve like this, but I could also describe this curve like this. R of t is, and what What's x? What's y? Right. I mean, this vector valued notation was just a more sophisticated way of writing parametric equations, perhaps. All right, hold on now. The old arc length S was the integral of the magnitude of r prime of t dt. Now that was discussed. I don't know if I ever tested you on it. Maybe not, hardly at all. But that was discussed briefly back in chapter 12. Yeah, it was a little bit on your take-home quiz and stuff. It was discussed a little bit. But now check this out. If I want ds, that's s. So ds is like the derivative of s. So guess what? ds is kind of like the derivative of the other side, and the derivative of the integral sort of knocks out the integral. So it turns out that ds is this, the magnitude of r prime of t dt. That's the ds. That's what you need in this integral. And so by the time you go calculate this ds, it ends up with a dt on it. You're in t's and you got a dt here instead of a ds. Now I wrote it like that. Now, what does that really mean here? Let's write it a different way. It is this, the magnitude of r prime of t. If this is r of t, r prime would be x prime, y prime. I mean, I don't want to do it specifically for this. R prime would be 1 and 1, right? But hold on. It would be x prime of t, y prime of t in general. And then the magnitude would be the square root of that x prime of t squared and y prime of t squared. Are you guys okay? dt. I mean, that's what that is. That's what that is. So I need that. I need that little ds for this right here. So that means I need x prime and y prime. Again, I can talk like this or I can talk like this. I really hate to sit here and do both all day long. Let's just ignore the r for a second. I need x prime and y prime. What's x prime? 1. What's y prime? 1. Can you find ds then for this problem? ds would be the square root of 1 squared plus 1 squared. Thank you. ds would be the square root of 2 dt. So for this C1, the ds is the square root of 2 dt. Now I'm pausing. We totally set up that first integral for C1. It's kind of a lot of work, isn't it? A lot of little, I mean, nothing I did was too hard or too difficult, but a lot of little things you got to put together, little pieces you put together here. You need the curve. You need the derivative of that parametrization because that derivative leads you to ds. You need the bounds. The parametrization, the derivative of those parameters, the ds, the bounds. Then you change that whole thing. That whole thing, you just turn it all into t's. This whole problem got turned into t's. Let's work on our C2. For C2, I need a different parametrization. Let's see, this is a big mess here. I'll do it right here. C2. I'm going to work on my C2 parameterization. Here it is. C2 goes right here from here to here. Look at it. It's a real easy horizontal line. But how do we parameterize a horizontal line? We haven't done it in a while, so we got to recall some of this. I think I'd let x, let's see. What's going on?
Y should equal 2.
He says y should equal 2. That's a good observation. It looks like y is stuck on 2. And since it's moving horizontally, I guess x is the variable, so x is t. We'll let x be t, and y is stuck on 2. We'll let x be t, and y is stuck on 2. And then since x is t, what does coming up with the bounds for t, it really amounts to what are the bounds for x? Because x is t, x is going from 2 to 4? Well, if x is going from 2 to 4 and x equals t, I guess t should go from 2 to 4. Good. That's the parameterization for this curve C2. And now I would like x prime and y prime, please. X prime is 1. Y prime is 0. What do you think the ds would be then? The ds would be the square root of 1 squared plus 0 squared, or simply 1 dt. Hey, I'm done, right? That's all the work, that's all the necessary sort of pre-work. That's all sort of the parameterization for C2. Now we can go set up this integral. Okay, so the integral for C2, you're integrating that same function, but you're on a different path, and so you have different parameters. This time, over here, x was t, y was t, that was for C1. On this one, x is t and y is 2, so I'm going to have t squared plus 4. This time the ds is different. Last time the ds was this. This time the ds is actually just dt. And my bounds are 2 to 4. Are you guys okay? That's good stuff. Setting up the integral. Setting up a line integral. Parameterizing the curve. And setting up the line integral. It's good stuff. Now, if I want to finish the problem, of course, I got to integrate. You guys are good at that. You can finish this yourself. I'll help you, though. It is a 2t squared with a square root of 2. That's 2 square roots of 2t squared. I need to integrate that. I guess I'll get t cubed over 3. 2/3 square root of 2 t cubed. From 0 to 2, I'll plug in a 2 and I'll get 8. And I'm kind of done. I get an 8. I get 16 square roots of 2 over 3. I guess. Plus, I'm working on this integral. This would be, I need to integrate these guys. 1/3 t cubed plus 4t from 2 to 4. Okay, 64/3 plus 16 minus 8/3 plus 8. All right. That's 56/3 plus 8. I think I get 80/3. I think I get 80/3.
Yep.
So this is 80/3. The total answer, though, is that integral plus that integral. So there's the final answer here. We'll just call it 16 square roots of 2 plus 8, 80, all over 3. And that was good stuff. That's good. That's good stuff. A line integral. You had to bust it into 2 pieces. You had to. You had to bust it into 2 pieces, do 2 different line integrals, parameterize each curve, know what the ds is, know how to do all this. This is good. How many times can I say this is good stuff? This is good stuff. I'm going to say it forever. Yeah.
In the second integral, can the parameters, since it's a line and it's never changing, can you have analyzed from 0 to 2 instead of 2 to 4?
No.
No.
It was a line,
No.
but it was going from, it started here and ended here. I mean, it was from here to here. And when we parameterized it like this, see, how do I get it to start at 2, 2? I need to let t start at, to get it to start at the point 2, 2, x needs to start at 2. And if x needs to start at 2, t needs to start at 2 and go to 4. So x has to go from 2 to 4 according to this picture, and so therefore t has to go from 2 to 4. Okay. Yeah. I was kind of waiting for this question, which is, okay, cool, man, you did this line integral, you got this number, you got this answer, which is a number.
What does the number mean?
What does it mean, right? Well, okay, I can tell you, but I kind of don't want to. The truth is, remember, what we're learning about is two different kinds of line integrals in this chapter. So I did this one first. The book starts with this one, then we do move to that one. I can make up a meaning for this, or I can come up with a meaning for this, but he's not the most important one. And so there's a couple different ways to interpret the meaning of this, but I kind of don't care. He does show up on the test in just a couple places, but this one shows up on the test 7 or 8 times, a bunch of times. And this one has some important physical meaning, and this one I'm saying doesn't, but it kind of does So now do you want to know the meaning after I poo-pooed it like that? I'll tell you one meaning. There's some problems. Here's one. They say maybe this curve is a wire. Maybe this curve is a wire with a changing density, and this function is the density of the wire at any time. This function is the density function for this wire. Like maybe it's made out of tin and then gold and then wood and then lead and then I never heard of a wooden wire, but anyway, it's a wire with a changing density, and when we integrate along its curve, we have just calculated the total mass of the wire. So if this is a density graph, we've calculated the total mass of the wire. I mean, I could try to explain that better, but that's one use of this they come up with in the book. Again, it's a little bit contrived. Here's another one though. Here's a geometrical meaning for this. You know, I'm integrating a 3D. You know, this is z. Z equals. There's a 3D function living up above this curve. And technically, here's what we did. We integrated over this curve. So it's kind of like, this is z. It's kind of like I found the height over this point, the height over this point, the height over this point, the height over, and I added up all. It's really like I did what they call lateral surface area. It's like there's a wall here. There's a wall here up to this function. So the height of the wall is this function. What function? Oh, this function. The height of the wall is this function. And there's just a very thin wall there, and we calculated the height of the wall times the distance of the wall. We calculated the area of the wall, actually. What's called lateral surface area. Does that make sense to you? I mean, there's a good picture in the book. Hang on, what would this look like? This curve is this, and then it's this. That's the curve. And then there's a function up here, so maybe, oh my goodness, oh my goodness. Oh my goodness. I mean, maybe there's that wall, and then, Jesus, how do I do this? Then there's maybe this wall here.
Roller coaster.
Maybe the supports of the roller coaster, right? The area underneath the roller coaster. Yeah, I don't know. Lateral surface area. There's some good pictures in the book. But again, I don't want to get hung up on the meaning of this guy. But I want you to be able to do this guy. Okay. Maybe we should do this other guy. And maybe I'll go ahead and tell you his meaning. This is an important physical meaning. This is the work. The work. That's a physics concept. By the way, work is energy. Work is energy. It's the work done by the force field. See, it's physics if the vector field is a force field representing forces. Forces do work. That's a correct way to talk. Forces do work. So it's the work done by the force field, F, on a particle. I guess you could say on a little particle. You're doing work on a little particle as it travels the path C, see again, I'm integrating over a curve. And the curve is the path through this force field. So it is the work done by the force field on a little particle as it travels the path C through the force field. Pretty cool, huh? Now, I didn't derive this for you. I didn't, the book sort of explains why that is what it is. I'm just telling you that is what it is. That's what it is. And if the path is kind of going with the force field, so we looked at vector fields yesterday. There's these arrows in 2D or in 3D. And if the path is kind of going with the force field, I think the work comes out to be positive. If you're kind of going against the force field, the work comes out negative. If you're kind of on some path where you kind of go with it and then you kind of go against it, it's possible the net result of all the work is 0. That's possible. So you can get any kind of answer for this, positive or negative or 0, and it kind of means something when you get those answers. Yeah, so cool. Let's do one of those problems. Let's get rid of this. Let's do one of those problems. All right, so what do I got to do one of those problems? To do one of those problems, I got to give you a vector field, okay? I think I'll give you a vector field here. I'm making this up, so this could be weird. X squared y squared minus 2x, comma, 3y cubed plus 4xy. Oh boy. And now I need to give you a curve. I need to say that I'm working on this curve. Look at this. This curve is y equals x squared is this curve. From -1 to 2 on the x-axis. Or I could label this point -1, 1, and I can label this point 2, 4. And I should put little arrows that show you that you're going this way. Because when you set up the parametrization, you got to go the correct way. If you do this problem and go backwards, I think you get the negative answer. You get the wrong answer. And maybe it's the negative of itself. All right, so what do? I think, again, the way we tend to work with these problems is we turn this all into t's. We turn this whole problem into t's. So, notice also what you got here. You do have two vectors in this problem, and there is a dot product between. We're dot producting these two vectors. Okay, here we go. I'm going to try to set this up. Well, first of all, I need the parameterization for this curve. How would you parameterize this curve? I mean, here's what's called the rectangular equation. It's up to you to parameterize it.
Then x equals t.
The easiest, almost always best way to parameterize something is let x equal t. And if you let x equal t, then the result is y equals t squared. Now that's not always true. If you're going around a circle, then I think sometimes it's good to let x be cos t and y be sine t. Or, if you're doing circular motion, those were my parametric equations for circular motion, if you remember. But anyway, this is cool. But now that I'm definitely up in this integral, I think I want to use my R notation, my vector. So instead of writing parametric equations, I'm going to switch to this R of t notation. And what would I call this? T squared. But what I really need is dr, which is, it's kind of like this. It's dr dt. It's the derivative of r with respect to t, which would be what? 1, 2t. But the reason it says just dr is because guess what you do with this dt? you kind of multiply it and it shows up over here. So dr is 1, 2t dt. So we got our dr. I'm ready, man. I'm gonna set up this integral here. What about my f? What do I do with f? And my f's kind of nasty. What is my f? Oh, there it is. Yeah, big, terrible, nasty f. And it's all in x's and y's. It's a 2D vector field in x's and y's. It'd be cool if you could see the vector field. There's vectors shooting all over the place here. There's a vector field, and we're trying to travel this path through the vector field. I'm sorry you can't see it. If we had some cool technology, I could type it in the computer. We could see it real quick. But anyway, there's a vector field here. I mean, you know what? I mean, I don't know what it is, but I just want to pretend I can. There's a vector field here. Short vectors, long vectors, short, pointing in all kinds of different directions. And I'm a little particle traveling through this vector field on this path. Anyway, when you set up this integral, you switch it all into t's. So you take these x's and y's and replace them. Now, how do you replace them? Oh, by what they were. And there they are parametrically, or there they are parametrically. So either way here, that's x and that's y. And I should replace every x with a t and every y with a t squared. And see what I got here. Okay. So hang on, x is a t, so that's t squared. That's t to the fourth, isn't it? Minus a 2t, comma. Oh my God, what's that? T to the sixth? That's t to the sixth. That's a 4, and that's a t, and then that's a t squared. Here, let me just clean that up a little better here. What is this? This is a t to the sixth minus 2t, comma, 3t to the sixth plus 4t cubed. Are you with me? This is my vector field with the t's filled in from our curve. From the curve that was described here, the parametrization of the curve filled into the vector field there. Awesome. I need to dot product that vector field. Dot product that vector field with dr. That's what the original problem says. Where's dr? Here it is. 1, comma, 2t dt. That's it, you guys. That's the setup. Oh, wait, I need some bounds. Everything's in t's. The bounds should be in t's. It's easy when x is t. Whatever the bounds for x are the bounds for t. When x is t, whatever x does, that's what t does. So that's nice. But and what does x do? -1 to 2. So t goes from -1 to 2. Right? I could have sort of said that here. -1 to 2, but I needed it here. Cool, you guys. That's it. Let's do it. It's a dot product, and then it's an integral. I mean, but you do a dot product first, which you know what that means, I hope. You multiply this times the 1, so t to the 6 minus 2t, plus this times the 2t, which I'll do a little bit of that in my head. When I multiply that times 2t, I get 6t to the 7th and 8t to the 4th, I think. And that's all added together. It's no longer a vector now. The dot product is a scalar. And you will now integrate from -1 to 2. Good luck.
Easy peasy.
I mean, it's a little tedious, but it is easy, but it's tedious. I'll help you do it real quick. 1/7 t to the 7th minus t squared plus 3/4 t to the 8th plus 8/5 t to the 5th. Wow. All right, all you got to do is plug in your -1 and 2. Oh my God. You guys are crazy. What's 2 to the 7th? 128. 128 sevenths minus 4 plus, oh my God, 192 plus, oh my goodness, 256 fifths. I think I'm doing good. Minus, now I got to plug in the -1, which is really fun. -1/7. -1. +3/4. And -8/5, I think. When you plug in that -1 to 2. Yeah, if anybody helps me add up those fractions, I'd appreciate it. But then there's a final answer here. And the final answer is the work done by the force field on a particle as it travels through. And work is energy, so it's the amount of energy needed.
I got 36327 over 140.
Thank you. Now just make that a decimal for me.
259.48.
Okay, it's all positive though, huh?
Yeah.
Okay,
Does
cool.
that seem right?
Yeah, I got
That's what you got? Okay.
Thank you. Thank you. Any questions? I mean, to me, I don't know, at some point.
What are the units in that?
Yeah, right. I mean, it is a math problem. It's kind of unitless. But if it's work, maybe we kind of know work is
Joules or foot-pounds?
well, right. Work is force times distance. So sometimes they say Newton meters. You said foot pounds, which is pound
The
feet.
math you normally use it.
Pound feet, that's right, or foot pounds. But then I said it's equivalent to energy, and so it is joules. I mean, there's a kind of a long conversion process to get from Newton meters to joules, but it is, or it's equivalent, or maybe even calories, or I mean, whatever energy is. So yeah, it's energy or work. Energy or work. And, you know, what's a little funny is this way it's worded and the way, I mean, I'm not a physics teacher, you know, I'm a math teacher, but, so I'm not real comfortable with certain physical things. What was I going to say? The fact that it came out positive kind of means that the vector field was kind of with the direction of motion, which is kind of like what I drew. The vector field was sort of with the direction of motion. It came out positive. When it comes out negative, that means most of the vectors were kind of against the direction of motion. You know, but sometimes I like to think maybe of the vector field as like a river. You can think of it as a river and crazy currents in the river. You know, that's the vector field. And then I'm a little particle that tries to swim against the current or with the current or whatever. You know, so then I'm swimming. I'm trying to follow this path as I swim through this river. And so then I feel like I'm the one doing the work. You know, which is not really the way it's worded. You know, I mean, but, so I often kind of misinterpret this, I think. I mean, I'm about to share my misinterpretation with you, which is that I'm a little guy swimming across the river. I got to do a bunch of damn work to get through this river. But that ain't true. I'm not doing the work. The work is being done on me, kind of the work done by the river on me so maybe I just float. And but somehow, maybe I'm tethered to this path, or I got to stay on this path. And as I float down this path, I mean, it's probably accelerating me, right? If it's with me, it's performing work on me. I'm probably accelerating through this path, maybe. I don't know. It's just hard for me to. The work done by the force field on particle as it travels this path. I'm trying to put that in other words. It's kind of hard to put it in any other words. But it's not the work done by me, or it's not the work done by the particle, which is, I tend to fall into that trap. That's bad. That's not what's going on. Okay, let's try another one. Let's just try another random problem. Let's do this vector field. Let me think here. Yeah, let's do this vector field. Negative 3y, 4x. That's my vector field. That's kind of strange, little easy vector field. And then here's my path. My path is a circle of radius 2. And I'm going counterclockwise on a circle of radius 2. So there's my path. That's my path. That's my vector field. And I want to find the work done by the vector field on the particle as it travels this path. So I need parametric equations for a circle of radius 2, centered at the origin. Parametric equations, written maybe as a vector valued function here.
Sine t, 2 sine t.
Good.
2 sine t.
Right, you may or may not recall this, but we did do this a little bit in chapter 12 and kind of chapter 10. A circle of radius 2 should be 2 cos t, 2 sine t. And if you wanted to go counterclockwise, then you let x be cosine. So you let x be 2 cos t, and you let y be 2 sine t. That's the classic start here and go counterclockwise. Maybe what helps you remember that? Maybe just the kind of the basic old unit circle idea of x being cosine and y being sine might help you think that, because a unit circle sort of works this way. Start here, counterclockwise. So letting x be cosine, y be sine, that's classic. Hey, how much t do you need to complete this path?
2 pi.
Yeah, 0 to 2 pi. You're right. You know, if I wanted to mess with you, I could put a little number in there to mess with the period,
Change the period.
and then you'd have to come up with the correct shrunken period or whatever. Right. Okay. But anyway, this was a standard normal period. All right, well, then I think I'm ready to do this, aren't I? Well, I need r prime. I need dr. dr is r prime, and it's the derivative. What's that?
Negative 2 sine t.
2 sine t.
2 cosine t.
2 cosine t. Okay.
dt.
Yeah, with a little dt on the end. That's right. All right, here we go. We're going to set up this integral. So this integral it's always this. It's f dot dr. So it's f... By the way, it's 0 to 2 pi, I guess, once I get it all in t's. And it's f, but it's f written in terms of t, and so the y is going to become
Negative 6 sine t.
2 sine t is the y, so that's a negative 6 sine t, all right, comma, that's a 4 times 2, the x is 2 cos t, so that's 8 cos t, huh? All right, dot product with dr. What's dr? Negative 2 sine t, comma, 2 cos t. All right, now I'm starting to see something I might not like, but that's okay. I just think I could have made this problem a little easier with some, now that I see it. Having these different coefficients is kind of messing with me here. Maybe I should have, if I could have kept these the same, I might have been a little happier. But, because watch what happens. I do this, so now I do the dot product. I'm just looking ahead to the dot product. If I do the dot product, I get 12 sine squared t plus 16 cos squared t dt. You know, if I would have had both of them be 12s or both of them be 16s, I could have used the good old identity. It would have been sine squared plus cosine squared would have been a 1 times 12. I mean, I could have factored out the 12. Yeah. Anyway, I didn't do that. So since I didn't do that, you can. Well, does anybody know how to integrate a sine squared?
It's not sine 2t over 2. It's 1 plus cosine 2t over 2. 1 minus.
No, that's cosine. Cosine is 1 minus cosine 2t, right?
It'll be 2 sine theta.
You're doubling them? The half angle, that one.
We use have to.
Yeah.
Okay, so you're right. You're saying that, right, the way you integrate a sine squared is you have to use a half angle formula. And so you change it into 1/2, 1 minus, I think it's minus, cosine 2t. You turn it into that, then you can integrate fairly easily. And how do you do a cos squared? Again, it's called a half angle formula. You turn it into 1/2, 1 plus cos 2t. So I guess I could try to knock out a couple half angle formulas here. Yeah, let's just do it like that, I guess. I should just do that. But this was back in Cal 2. I don't know why. I mean, it's just an identity, but I mean, we could have taught it to you in Cal 1, but at some point somebody needs to tell you that when you integrate sine squared or cosine squared, you use this identity. That's how you do it. Now wait a minute, I haven't integrated. You use this identity, then you integrate this guy. You integrate these guys. But it was taught to you kind of in section 8.3 in Cal 2. But anyway, so I'll apply that here. Let's try this. 0 to 2 pi. You're saying this is going to be 12, and then I'm going to have sine squared. So that's going to be 1/2 1 minus cosine 2t. So ultimately, it's a 6 there. Okay, and then this is 16, and then it's 1/2 1 plus cosine 2t. All right, well this might not be too bad. If I distribute, multiply, yeah, that was a 6. If I distribute it, it's 6 minus 6 cos 2t. This is an 8. If I distribute it, it's an 8 plus 8 cos 2t. Okay, you can gather a couple like terms together. It's a 14 plus 2 cosine 2t. Yeah, that's it. And now I can try to integrate this, finally, with respect to, t, from 0 to 2 pi. You guys okay?
Mm-hmm.
All right. So now, how do you integrate a 14?
14t.
14t. 14t. How do you integrate a cos 2t?
Just sine 2t.
The integral of cos 2t is sine 2t. Technically, it'll spit out a 1/2. You're going to do a little u substitution. It spits out a half and kills that 2. So you're saying the answer is sine 2t. That's true. Did a little bit of that in my head. You don't have to do it in your head, but that's it. So that's it. That's the answer from 0 to 2 pi. Here comes the fun part. Plugging in a 2 pi gives you 28 pi minus, plus, when you plug a 2 pi in there, the sine of 4 pi is 0. Minus, when you plug a 0 in there, that's a 0. And when you plug a 0 into the sine function, that's a 0. So we're cool. We're all done. Even if I wouldn't have integrated those signs, well, anyway, the answer is 28 pi. Wow, that was a pretty good problem. Again, a positive amount of work. I don't know what does that mean? It means that I was kind of with the vector field, at least for the most part. There might have been some positive work and negative work done during this path, but the net result was positive. Doesn't mean it was all positive. Anyway, that's pretty good. I guess today's our little shorter class, and so I guess we're kind of finished. that is good, you guys. I'll see you Friday. Might move into 15.3 a little bit, which is similar stuff.